Hello, and welcome to today's webinar, brought to you by Laser Focus World and Endeavor Business Media. Today's event, Laser Myths, What You Don't Know Can Hurt Your Process, great title, will be presented by John Mccauley, Business Development Manager at Ophir. My name is John Wallace, and I'll be your moderator today. This presentation is both live and interactive, so you can ask questions at any time via the Ask a Question box in the presentation window. We'll answer as many of these questions as we can during the Q&A portion at the end of the presentation, after the presentation. If you have any technical difficulties during the webinar, just type your issue into the Ask a Question box and a member of our team will assist you. A reminder email message will be sent to all registrants with a link to the archive, and this link will also be accessible from the Laser Focus World website. Also, for your convenience, for the on-demand version of this webinar, which you'll be able to view within 24 hours of this live event, we'll provide a PDF of the presentation that you can download using the Event Resources tab. Now it gives me great pleasure to introduce our speaker, John Mccauley.
Hello, John. As always, it's a pleasure working with you and everybody at Laser Focus World for this medium to communicate to this very important topic. So I do certainly want to thank you for this platform to speak. I want to thank Shannon Toon, who works behind the scenes tirelessly to make these events happen. So I certainly want to recognize her good work as well. And thank you all for this opportunity to speak. I'm John Mccauley. I'm a Senior Business Development Manager for Ophir. We manufacture products and solutions in laser performance measurement, laser power meters, laser beam profilers. We are part of MKS Instruments Corporation, part of the Motion Photonics and Optics group there under Innovative Solutions. And there's a little bit about our parent company. You know, we're all here today. It certainly does say something about you that you are John, I think your microphone, there we go. It certainly does say something about you that you have taken time out of your busy day to join me and, you know, in an effort to make your laser processes better and to maintain the high quality processes that you are involved with today. And certainly it is my wish that I can pass on some information to you that will help you with respect to that. But just to kind of frame the conversation today, I just start off by saying the application of lasers for material processing is becoming more commonplace in industry. If it really is kind of amazing if you think about it, all the places where a laser is used to manufacture the goods and the services that we are involved with. Lasers are being used more and more every day, and the applications of the laser seems to be endless. But as industrial laser processing, which is what we're talking about today, as processes advance, so does laser technology. The laser certainly has evolved over the year. The cells in which the laser is used, the processes in which they're being used, have all evolved right along with the laser. But sometimes, and this is kind of where we'll bring us to the topic of conversation today. Sometimes there are some myths that are generated, and sometimes there are some mindsets that are held over from some of the legacy technologies when it comes to laser processes and laser sources. Still several myths surrounding the application, employment, the operation, and maintenance of lasers. The laser is an invisible tool. Oftentimes, people treat it like this magical black box. They want to come in and load a part and press the button, but not really, very interested in fully understanding how this laser light does its job with respect to what it's designed to do. They just kind of hope that it does what it's supposed to do, and they're not really. A lot of people are just not very interested in learning anything past that. But they really are, in that case, kind of doing themselves a disservice and not understanding how that light is, a very beneficial tool in their process. How the light behaves in material process. What is actually the light doing? How modern lasers different from legacy products? How these lasers have evolved over time, and what that means to the laser operator, and how they maintain and operate that laser system. And then when and where measuring laser performance is, it's nice to have at this point, or is it important, very important to measure my laser at this point? Or is it absolutely critical to measure my laser at this point? Those are some of the topics that we're going to be talking about today. So separating fact from fiction, separating these myths from what is actually going on is really kind of vital to ensuring that you have first of all, start off with a high quality laser process, and second of all, maintain that laser process at a high quality. So that's really why we're here today. So, when we talk about the maintenance, when we talk about the operation, when we talk about the purchase of a laser system, there are a lot of similarities between that and the purchase, the operation, and the maintenance of an automobile. So I'll try to tie a lot of these concepts to the operation of an automobile, because I think that's something that we can all relate to. We're all very familiar with. We've all purchased vehicles. We've all maintained them and operated them. So whenever possible, I'll be able to hopefully be able to tie that illustration into what I'm talking about to make the concepts a little easier. So what we're looking at here is a picture that I grabbed about 3 years ago. It is the dashboard for a Mercedes-Benz A-Class. At the time, I think it was a concept. I'll be honest with you, I don't know much about Mercedes-Benz cars. Ophir just simply doesn't pay me that much. But anyway, so I assume that this is very similar to the way dashboards are looking at today. So if we take a look at this dashboard, we can start to get an idea of the types of information that we get from this dashboard. There's information that is vital to its operation. There's information that's nice to have as far as its operation. There's information that's very helpful to its operation. We start to look at all these things that we read. We've got the speedometer, the tachometer, the odometer, the fuel lights, the engine lights. We got GPS. We have phone. We have all this information that we're kind of almost being bombarded with. And again, a lot of it is very, very useful to the operation of this vehicle. A lot of it is vital to the operation of this vehicle. A lot of it is vital and useful when it comes to the maintenance of this vehicle. But we have a lot of, we've just grown used to having a lot of information being presented to us. And that's kind of the way we, in this day and age, operate and maintain a vehicle. We'd like to have this information. We'd like to know how our car is performing. We'd like to know when maintenance items are relevant. So let's rewind a little bit. Let's go back about 100 years. Now we're looking at the dashboard for a 1925 Ford Model T. And if you look at this dashboard, it's you can probably use your detective skills and figure out, well, John, this is a very different dashboard from the modern day Mercedes-Benz A-Class. And you would be right in that. So we look at the information that this dashboard gives us. And if you look really close, you can see battery current. That's the only bit of information that I think was vital to have in 1925 for the operation of this vehicle. So can you operate this vehicle today? Yeah, you can operate this vehicle. I suppose it's still legal to operate a vehicle without a speedometer and everything else. But it would be, for us in this day and age, it would be very difficult to have this vehicle and to operate it just from an operation standpoint. As a daily driver, imagine driving this car back and forth to work every day. Apart from its performance, that's another. But as far as just the operation of the vehicle, there's just no information other than battery current that you're being supplied with as far as how this vehicle is operating and how and when you must maintain this vehicle. So we look at these two dashboards side by side. Would we operate the vehicle today without a speedometer? Could you operate? Yes, you could operate the vehicle without a speedometer. You could eventually tell from when the policeman pulls you over and says, "Hey, I clocked you at 90 in this 55." That's when you would learn what speed you're going up, and you wouldn't have to operate with a speedometer. Could you operate without a fuel gauge? Yes, you could operate the vehicles today without a fuel gauge. Would you want to? Yeah, you could drift over to the side of the road when you run out of gasoline, and that's when you know that you need fuel. Or you could drive with some kind of indicator that we have. It would be difficult for us to operate the car on the left. I think we can all agree. So why would we operate and maintain a laser system, which is more expensive? It makes you more money. Why would you operate that with the same mindset, not knowing how it's performing? So that's kind of what we're here to talk about today. You look at these two cars side by side, there's roughly 100 years difference. So there are a lot of changes, a lot of general changes that we'll talk about just in a second. Obviously, technology has changed. There's more stable performance. There's more of a creative engineering of the processes. So all the thousands of processes that go into the making of the modern day vehicle, those have evolved over the years, as well as the production environments that these vehicles are made in. They've become smarter. They've become more efficient. Just a lot of things have changed over the years, but there are some things that are similar between these two vehicles. What's remains consistent? Both of these cars still must be maintained. They must be repaired. Automobiles are still made up of physical matter, things that you can touch. And because of that, there's going to be, catastrophic failures. There's going to be, changes that happen because of just being made up of physical matter. Also, the production environment or the operation environments in which these two cars are going to operate in haven't really changed that much in 100 years. Very, very harsh operating environments. So, sand and wind and heat and snow and cold and rain, all these things take a toll on the vehicle, which affects its maintenance and its operation as well. So tie that to the example of what we're talking about here today. What's changed with lasers over the years? There's been material advancements. The materials that are going into these processes have changed, have become more sophisticated. The laser sources have become more stable over the years, just as technology gets better. There's been more creative engineering of the work cells. Systems integrators are doing a fantastic job with taking some of the problems that have evolved over the years and solving those problems in the work cells. Much smarter production environments and much smarter from the collection of data in some cases, and allowing you to make those processes smarter. But there's also things that haven't changed, very similar to those cars. The applications of the lasers are always going to be pushed. The operational parameters are always going to be pushed. Faster cycle times are attempting to be achieved, so you can get parts out the door quicker. Quality is attempting to be, increased or at least maintained at the same level. Lasers and laser systems are still made up of physical matter. There's still going to be those failures, those sometimes catastrophic failures of components just because of the systems are made up of physical matter. Also, the very similar to the automobile, the harsh production environments that these lasers operate in sometimes have very catastrophic effects on the laser system. They must be dealt with in such a way that they don't drastically change the performance of the laser. But having said that, laser systems will naturally decrease in efficiency over time. It's very important, I'll make the case today, that through the measurement of its performance, that's when you know how and when to take proper actions on your laser system when those changes take place. Okay, If I could take your car, and if I could, with respect to the maintenance of your car, put that battery current thing on your dashboard and have you have that be your indicator on your laser system of when the laser must take action, what would that one single laser parameter be? And that is the idea of power density. So what is power density? I like to define power density just in a general term, the measure of how the laser is being applied to the material that is processed. It's really where the rubber meets the road with respect to laser processing, is where the laser light meets the material that it's processing. That is really how the laser is defined with respect to how that laser is going to interact with the material that's being processed. Power density must be maintained regardless of the laser application. And what I mean by that is it doesn't matter if you're using a laser for welding, for brazing, for cutting, for marking, for heating. The intended result of the laser requires some kind of power density. And the power density is defined by two laser performance characteristics. It's expressed in this expression, watts per centimeter squared. You see in the top of this expression, the laser power. The laser power is the W, it's the watts. It's the amount of laser light that's being applied to the process. The bottom of the expression is centimeter squared. This represents the beam size, the spot size, the focus spot size. It's called several different change, but it's the amount of laser light that's being focused down to the process. And those two characteristics are going to define how that laser interacts with the intended process to have the intended result. How do each of these laser parameters change how the laser processes the material? So say you turn on your laser day one, you've got 4 kilowatts, you measure 4 kilowatts at the process. 3 years later, you take a power measurement and you've got 3.5 kilowatts. Well, what's that going to do to your power density? It's going to decrease your power density. It's going to decrease the efficiency of how that laser is processing the material. The same thing as far as changes in focus spot size. Or the beam size being applied. There are sometimes what's called a thermal effect that happens on your laser system that causes the location of the focus spot to drift upwards. So now instead of focusing down on the process, you have a focus spot that is drifting off of the process. What's that doing at your work plane? It's increasing the beam size at your work spot. So that is increasing the beam size at your process, which is going to what? To the power density, it's going to decrease your overall power density. It's going to, again, reduce the efficiency of that laser process. All right, so we come to the myths. I'd like to share with you 5 myths, 5 things that's been told to me over the years with respect to laser performance and why or why not you should measure your laser. Okay, so myth number 1, our laser is very new and very stable. Measuring laser performance isn't necessary. Okay, so getting back to the automobile, this is oftentimes a mindset that we can adapt when purchasing a new car. Hey, I've bought the new car. I'm in the driver's seat. I can smell it. I'm driving down the road. Nothing can stop me. Nothing can go wrong with this new car. But how oftentimes have you heard a story where something goes wrong with a new car? It does happen, unfortunately. We have put a lot of faith into the manufacturing of that car when we buy a new car. But the fact of the matter is oftentimes things can go wrong, even though most times they don't. So let's address this myth. No matter how a laser is being used, the success of a laser process depends on how the laser is performing. Okay, regardless of where in the life cycle that laser is, the performance of that laser is going to be directly related to how that laser is going to process process the material that is being processed. So I'm asked this question quite a bit: when should a laser be measured? And I think by that question, people usually mean, how often should I measure my laser? Should I measure it 3 times a week, 4 times a year? How often should you measure the laser? It's a fair question. Bottom line is, what it comes down to is, how often do you think it should be measured? What I would suggest is, if you have purchased a laser system and you have spent all this money on it, you want to make sure that it is operating as it is designed to operate, since you just spent that much money on it. Oftentimes during the runoff of a system and a system delivery, there will be laser measurements that are performed. Try to get a baseline or how that laser is performing once it's delivered to the floor, so in the event that you do have either process drift or you have some catastrophic event happen to the laser, you can go back to those baseline measurements and make sure that the laser is operating as it is intended to operate. But I would measure it very frequently once you first get it, and then once you have an understanding of the trends of those laser performance characteristics, you can back off on your measurements and measure them once a quarter. I've got customers who do laser measurements 3 times a day, once per shift. So it really just comes down to the weld processes or the processes that you have developed. Ensuring consistent laser performance is really crucial throughout a laser's life. So if you look at the laser with respect to the growing up of a human being, you have the source development. You have the people who are developing the sources. They're doing a really good job at collecting the information on how that laser performs. The laser power, they have to verify that and communicate that to their customers. Same thing has to do with the beam size, the beam shape, the engineered beam shape. M squared is also a measurement that needs to be measured when developing a source, just so those laser quality and laser performance characteristics can be communicated to the customer. Once that laser is used for the application development, laser performance characteristics should be captured as well, so that when the application is developed, the application engineer can say, hey, here's the end result of the process. Here are the laser performance characteristics that we came up with. Here's how your laser looks at the time that this application was developed. When that laser source is integrated into a system measurements should be taken just to make sure that the laser is performing with consistency between the application development and the integration of the system. And then finally, once the laser is put into production, those bench line measurements, like I mentioned a second ago, should be taken, so that if laser maintenance needs to happen, or if some kind of process drift, you get an operator who just changes laser parameters for whatever reason, if something like that happens, you can come back to those bench line measurements. So those measurements are very crucial in my mind, and very important to take with respect to the lifetime of that laser. I'll make this statement: only through laser performance characteristic measurement and through the analysis of the trends of these characteristics can you really fully understand how the process is stable over long periods of time. Okay, and I think that's probably realized by most everybody here. Myth number 2: when the process starts to drift, we just turn up the power and we keep going. This is a pretty ugly one. This is one I actually just I'm in the process of helping a customer with. Oftentimes there's this myth that when you lose power density, the laser's not performing the way it's engineered to. I'm not going to take a measurement on it. I'm just going to start to tweak on little things here and there. I'm going to turn up the power. I'm going to change the rep rate. I'm going to change the cut speed or whatever else to overcome these drifts in the process. I'm not going to actually solve the problem. I'm not going to get to the root of why this is happening. I'm just going to make tweaks on the process until I can get it to where the process is consistent. So if you're driving your automobile and you get an engine light, you take it to AutoZone, just clear the engine light. I just want to get the engine light. I just want to go on down the road. I think most families have been in the situation where, money is tight. You're not driving the best vehicles. And there was a time when our young family we had a minivan. It was a Chrysler Town and Country, and we had the engine light come on, and we went and checked it, and it was a problem with the CPU, some just random code that the CPU was throwing. And it was change the CPU for $1,500, and the only thing that's going to happen is the engine light is going to go off. So we drove that minivan with the engine light for years. We actually drove that minivan with the engine light so long, the engine light actually burned out. So we're just like, all right, the engine light is gone. So, oftentimes we operate the vehicle like that. I don't want to worry about the maintenance. I just want to keep driving the car. So obviously, I think, we can all agree that if we treat our lasers like that, with that mindset, we're ultimately going to get into a situation that it's going to be very, very costly. When we talk about how the laser system is set up, it's, we talked about the laser source. There's been many different lasing mediums over the years: YAG, fiber, direct diode, disc, CO2. You take that laser and you have some kind of delivery system from the source to the process. It's involved with bellows and process fibers and shutters, apertures. Purge gas can affect your laser. And then ultimately it's delivered to some kind of laser processing head, where you have some way that the laser is shaping that beam down to the process, sizing that beam down to the process for its its intended use. But if you look at all these components that the laser is touching, you can quickly see that each and every time a laser touches an object, it has the potential of changing in some way. Right, so you could start off with this nice, pretty, round Gaussian beam at the laser source, but once it touches these components, in this case it was a misaligned mirror, your beam starts to change. Right, your beam is not as efficient as it could be, and then finally, when it reaches your process, you've got this nice, I say nice, but it's kind of this ugly-looking beam that could process, but it's definitely not as efficient as it probably could be. There are a lot of reasons why a laser wouldn't operate as designed, regardless of how the laser is applied. There's cutting nozzles that are misaligned, as you can see in this picture. There are, there's faulty manufacturing of components. There's faulty components. I ran into this one time, improper maintenance, where the maintenance was not, performed as it should be. There's these environmental factors, the heat, the humidity, the operating environment is just dirty. Contaminated cooling water or purge gas, these can all affect the performance of the laser in some way. Kind of as a bonus myth, I'll tell you that oftentimes when I talk to fiber laser, relatively older fiber laser cutting people, they oftentimes have, they probably cut their teeth on a CO2 system at some point, and those maintenance practices have carried over into the fiber laser world. Well, I'll tell you that those optical components are very, very different, and the maintenance of a fiber laser today versus the maintenance of one of those CO2 systems is very different and should be treated as such. Those modern day optics of the 1 micron lasers are very delicate, and you just can't treat them with the robust optics that you could with a CO2 laser. So just a bonus myth for you. As long as the laser systems are susceptible to human error, which they will be, and physical limitations, which they will be, the performance of laser systems will change over time, usually not for the better. The laser, because it's a physical piece of matter, will always try to revert to its natural state, and eventually, some kind of some kind of maintenance will be required on your laser system. Changing process parameters and avoiding the problem, which is really what this is, with some kind of focus drift, is not an effective solution and really can be a costly decision. So just turning up the power over and over and over to the point where your process is drifted out of control is really not a very good way of maintaining your laser system. All right, myth number 3. Measuring laser performance is too costly, complicated, and time consuming. Okay, so Ophir, I've been in sales selling laser performance measurement equipment, and I'll tell you right now, this is a valid concern. This really is. This is not so much a myth, but I do want to talk about changes in laser performance measurement technology. So historically, laser measurement components have either been very expensive but very comprehensive, or relatively inexpensive but gives you an incomplete picture of how your laser is performing. By that I mean like single data points. Historically, they have been very complicated in the past. Just because of the older technology, they've sometimes been unstable in their performance. They've sometimes been delicate. You take lab equipment that was, equipment that's been designed to be in a lab environment. You take it to a harsh industrial environment, and you could have some problems with it just because of the change of environments. And oftentimes there's subjective measurement results. So one person might look at the results, hadn't come up with some conclusions based on their experiences. Somebody else may look at the measurements and come up with different set of conclusions based on their experience. We got a couple of examples here. You see to the right here, it's called what I call laser mode plate. It's just a phosphor coated plate that's illuminated with a black light. You shine a laser at it, you can see the laser shape, you can see how the laser is changing. But again, the result is based on the user's experience, and they're looking at that and they're saying, well, I need to do XYZ to my laser in order to make it right. Whereas a new person just starting off with lasers says, I have no idea what to do with that image. The image here in the middle is what's often known as a meat thermometer. You shine the laser at that chunk of black metal there, and you get a temperature, and that temperature correlates to how much laser is being output. Again, this is one single data point. It doesn't really paint the complete picture of what your laser is doing. So today, comparative to the historic laser measurement systems are of higher value. And notice I didn't say they're less expensive because oftentimes they're not less expensive, but they are of higher value because they bring very relevant, oftentimes real-time data on how your laser is performing, gives you the ability to trend that data over time, gives you the ability to log that data, to store that data, to compare that data. It's just the laser measurement systems today are of higher value. They're more comprehensive measurements. It gives you the ability to graph and to trend the data. They're much easier to operate, so they're much more robust in their design, intended to be used for industrial environments. They're just better performing just because of the advancements in technology. And also they have come with industry standard measurements. So there's no more guessing on how the laser should be performing. You are actually measuring the performance characteristics against a standard of measurements in most cases. So I want to present to you just some of our products to illustrate this point. This product is our Aerial. It's a standalone power measurement. It's intended to be used for those maintenance type situations. Very, very easy to use. I don't know how it could be any easier. You take it, you turn it on, you take it, you put it in the beam path, you fire the laser for just a second or two, and it'll tell you how much laser power was in that measurement. All right. It is a single data point, to my point earlier, but it is extremely easy to use. It is good. It does give you good relevant data on your laser performance. It does give you the ability to read the laser power on a nearby phone or PC through a Bluetooth interface. And as you can see, it display the laser power on the screen there. Very simple, very easy to use. This is an integrated power measurement solution intended to be integrated into a laser cell permanently. It is a water-cooled system. It reads up to 10 kilowatts. It'll either give you a go or no go. You know, you have laser light, you don't have laser light. You can use it as simply as that, or you can use it as sophisticatedly as, you know, fire the laser for several seconds, you know, up to a minute, just to trend what your laser is doing to ensure that you have a nice, healthy laser that's designed to be operating at those operational parameters with respect to power. It does have an optional shutter you see at the top image there, and it comes with a communication box that, you know, communicates with your production environment, whether it be Ethernet IP, Profinet, CC-Link, whatever your production environment is in. Here's another product. This is called the Beam Peak, and it is a standalone maintenance tool. I guess it could be integrated into a cell, but honestly, with respect to beam profiling and power measurement simultaneously, I don't think we've ever come up with a device that is as simple as this. It is literally a black box. You put it in the beam path, you fire the laser, and as soon as you fire the laser, you're getting real-time data on your beam size, your beam shape, your beam geometry. It does have an onboard power meter, so you're getting a simultaneous power reading as well, which will allow you to calculate a real-time power density measurement as well. Very simple, very easy product to use. It's got it does have a consumable, a beam dumps, where the beam dump is taking the brunt of the laser power. And then finally, this is a product called the BeamWatch Integrated. This is another device that's intended to be integrated into a laser cell. This also has integrated laser power meter, as well as your beam profiling data. The beauty about this device is this is a dynamic laser focus shift measurement device. So it will tell you, number one, it'll tell you where your focus spot is located. And if there are any changes to the location of the focus spot, it will tell you not only how far the focus spot is drifting, but it will tell you how quickly the focus spot is drifting. So it'll give you a more comprehensive way of how your laser is performing. And so you can know for sure when to take action on your laser based on those measurements. Okay, myth number 4. We're quickly coming to the end here. Myth number 4, laser processing can be managed just fine with or without laser measurements. Okay, this is, you know, it's a valid concern. It's a valid viewpoint, but I will make the argument today that without fully understanding the operational parameters of your laser, you can't really manage the process very well. Just like driving the car without the dashboard, you can drive your car without a dashboard with all that information that the car feeds back to the operator, but how do you know when to take maintenance? How do you know how fast you're going? How do you know when to fill up for fuel? You know, on an internal combustion. How do you know when to charge your vehicle, your electric vehicle? Without that dashboard, without that very important information, you know, you're just at a loss on how to fully, most effectively operate that piece of equipment. So historically, you know, there have been statements made to me like, you know, this laser process is so robust, there's rarely anything that goes wrong with it. It's a valid viewpoint. That's very, very true when a system is first run off, when a car is brand new, when a laser is brand new. It's a valid viewpoint, but because of the physical changes that's going to happen to your laser system, there are some changes that are going to take place. How do you know when to take maintenance if you're not taking measurements on your laser? This laser is welding sheet metal. Why would I care about its performance? You know, some lasers are used in a process that are very robust. They're tried and true. It's been done for decades. Why would I take measurements, you know, on this laser system? You take measurements on the laser system because it is going to change, number one, and you would need to know when to take action on your laser. But number two, it could be a situation where you are welding, you're making a weld to a safety critical component that requires some kind of validation of how the laser is performing. So safety must be made as far as the consideration as well. So personally, I believe that this mindset, this myth, I believe this is changing. This is kind of a, dare I say, old school mindset, but there are engineers coming down the pipe that have an appreciation for the collection of data. Industry 4.0 is driving this data-driven manufacturing. So engineers that not only have a desire to, but have a requirement to measure their process and to have as much data as they can fully appreciate that measuring your laser will give you will give you a better idea of how your process is performing. Safety and product reliability is and always has been a priority, but measuring a laser with respect to performance is really critical when you are processing these safety components, seat belts and bumpers. All these copper components that are being welded in the electric vehicles. It really is a safety concern if you don't know how your process, it is performing and know that it is performing consistently. Changes or improvements in technology calls for more critical monitoring of laser parameters. That's true. In addition to the change in mindset of the newer engineers, and increased material costs and environmental concerns cause more concern for scrap parts. In this economic age, it's getting more and more expensive to purchase materials, to find materials. The supply is, the relative supply is going down for the increased demand. It's just driving up costs. So the concern with scrapped products are causing engineers to take a closer look at monitoring system performance so that scrap is reduced. Really is a valid concern. And then finally, myth number 5, legacy laser measurement technologies are time tested and give us enough information about our laser. And this mindset, obviously, in my mind, goes back to someone who does have a lot of experience with maintaining a laser. Maybe they cut their teeth with CO2 cutting lasers and they're going into fiber lasers. They do have a lot of experience with how to maintain a laser, just a lot of tribal knowledge. And oftentimes they do use these legacy laser measurement technologies in order to measure the laser. And I say good for them. That's great that they have that knowledge and they have that experience. I want to bring up this picture again, this slide that we talked about earlier, and talk about 2 of the points. Historically, laser measurement has been inexpensive with an incomplete picture. Oftentimes they give you single data points like this meat thermometer here in the middle, or they give you subjective measurement results like this mode plate here. One person can see the mode plate and say, I need to do XYZ to this laser. Another person will take a look at the mode plate and say, I think that laser looks good. I don't think anything needs to be done. There's a disagreement. One person is right and one person is wrong. How can how can that conflict be resolved? Laser power measurement. This is a product called our Comet, made by Ophir. It's a relatively older, relatively inexpensive, very similar to that meat thermometer. You fire the laser for 30 seconds, you get a number based on how your laser is performing. It's good for its time. It's a good, quick and dirty check, but it does only give you one bit of information compared to this power meter system, which you have a sensor that you hold underneath the laser light or put underneath the laser light. Probably wouldn't hold it, and then you have a meter that's coupled up with that sensor. And this system, when you fire the laser for several seconds, it's going to give you a trend. It's going to let you know that the laser power has stabilized, or if it's going down, or if it's going up and down. It's going to give you some idea of what your laser is doing over longer periods of time, versus that one single data point. It's going to give you a dynamic laser measurement. So here is a laser that I captured data on. This was a 25 watt fiber marking laser. You see where the laser turned on, it took about, a little over 0.1 seconds to, or 0.1 minutes, just about 6 seconds or so to stabilize. But you see what it started to do once it started to stabilize. The power would drift down, it would come up, it would come up, it would stabilize, it would come down. You see a very, very inconsistent performance with respect to laser power. Well, think about what that mark would do if it was a minute-long mark. Say you were marking identification tracing with a 2D matrix or a barcode or something like that. What's happening to that laser mark if that laser power is going up and down? Well, ultimately you're gonna have an inconsistent mark. If you're marking a 2D matrix, then you could have a missed cell that's marked, and it's going to completely throw off that mark and cause it to not be readable, for instance. When we talk about laser beam profiling, we look at this relatively legacy technology, the acrylic mode burn. Acrylic blocks are very cheap. They're very portable. With tribal knowledge, it's very useful information. But again, it's only giving you one single data point. You fire the laser for 1 to 2 seconds into this block, you get a picture of what your laser is doing, a collective picture over that 2 seconds that the laser was on. It's a very incomplete picture of your laser performance. These are images. Compare that to a camera-based beam profiler, which will give you an instantaneous image of what your laser is doing. It will give you those industry standard measurements, but it'll also allow you to see what your laser is doing over longer periods of time. Are there any changes that are being, that are happening with your laser? This particular product is a beam profiling camera with product called the LBS 300, which is a laser beam splitter assembly, which attenuates the beam before it reaches the camera. So that's what you're seeing pictured here. I want to show you some images that I captured on a 5 kilowatt CO2 cutting laser and just try to illustrate this point. The laser turns on. It is of a certain shape. 1 second later, you see how dramatically different the laser beam is. It's much smaller. The beam shape is much smaller. And then it starts to increase in size, and it just starts to basically fall apart. So 2 seconds later, it starts to grow. 3 seconds later, you see a larger beam. 4 seconds, and then several seconds later, the beam has completely fallen apart. Well, think about what the laser is doing. What if this was a very long cut, for instance? What would the laser be doing? Well, the laser would be piercing. It would be starting to cut fine, but you can see, at about 3.5 to 4 seconds, because the shape of this laser is changing so much, you would completely lose the cut. Now, as a laser operator, you might be tempted, just turn up the power, just turn up the power. Well, I maintain in this case, the power is not the issue. The issue is that there is some kind of thermal effect on the laser system that's causing the beam to change shape. So turning up the laser the laser power may have the desired effect, but again, it's probably going to only have the desired effect for just a short amount of time before you really run into some problems. But without measuring your laser, you wouldn't have known your laser is doing this, and you might be tempted to, put off that maintenance. All right, so I like to end my presentations with a couple of quotes. The gentleman pictured here, his name is William Thomson. He was known as Lord Kelvin. He was a British scientist. He lived in the 1800s. He worked in the realm of science. So speaking of physical science, he made the statement that if you can't measure it, you can't improve it. Okay? Very true statement. If you have a process and you want to improve it, there's no way to improve on that process or that experiment or whatever you're doing. There's no way to improve on it unless you're measuring the results. That makes sense, right? Okay, compare that with this gentleman. His name is Peter Drucker. He was an American entrepreneur. He taught a lot of classes, just a very well-respected businessman. He lived in the 1900s. He was speaking of the efficiency of a workplace when he said, if you can't measure it, you can't manage it. So here are two different men lived at two different times, about 100 years apart, in two different realms, two different fields of study, and they're saying the same thing. If you want to improve on something, if you want to manage something, it's really impossible unless you're measuring it. You can't really manage or improve on something unless you're measuring its performance and know how to build on those results and with respect to the management and the improvement of your process. So, in summary, I think we've done a fairly good job tying our processes to the automobile. So the automobiles are monitored for performance and protected with maintenance. We do that for our automobiles. We have all this information coming back to us and letting us know when we can and should maintain our automobiles. Shouldn't we be treating our laser systems? Again, our laser systems are much more expensive. They can make us a whole lot more money than our cars do. Shouldn't we be having the same attitudes with our laser systems that we do with our automobiles? Laser technologies continue to advance and provide more stable processes, but laser systems will always be made of physical matter. And because of that fact, the result in changes in the physical matter will result in the way that the laser system operates. And again, going back to those quotes, if you don't measure those changes, you don't know really fully how to manage those changes or to improve that process. New laser systems are usually stable, but because of the second point, changes will happen. Benchmark laser performance measurements really do help you at a production stage to return the process to its intended state. As an example, laser measurements are taken during the source development, during the application development, during the integration of the laser system. At the production level, laser measurements really should continue on for this very reason, to make sure that the laser is performing consistently. When the process starts to degrade, when that process starts to drift, a comparison of laser measurements can be used to restore the process to the intended design. And then finally, while historically laser measurement solutions have been limited in their value and with the information that they supply, today's products, I think hopefully I've illustrated, provide the laser user with solutions which are much more comprehensive in their analysis, more durable in harsh environments, and really do give a higher rate of return on their investment that you will have. So, John, I'm going to turn it back over to you. Let's see, I'm going to get out of presentation mode here and see if there are any questions that, okay.
And thank you very much, John, for that thorough presentation. So we're now in the Q&A portion of the webinar. So once again, to ask a question, use the Ask a Question box in the presentation window. I see we have some questions already. First, what laser parameters are usually measured across the life cycle of the laser from application development to production?
Yeah, I kind of briefly touched on this, but there are, if you have a beam profiling system, you will see that there are quite a few laser parameters that you can measure. There's literally hundreds. So whittling that down to some useful laser characteristics that are worth measuring. Obviously, your laser power or your laser energy, if you're talking about pulsed lasers, that's very important to understand because that directly relates to how the laser performs at the process. So not only knowing your laser power, but also being able to, like I said, trend your laser data over longer periods of time to make sure that you have that flat curve, that very, very stable laser power. Or if you're talking about, again, pulse lasers, that your energy per pulse is going to be remaining consistent over time. Laser beam shape, like ellipticity, that's very important to measure because that's going to affect how your laser performs. So for instance, if you have an elliptical beam, one that's kind of squashed, measuring a shorter diameter versus the other axis, that's going to affect how your laser looks in a multi-directional weld, for instance. So if you have your laser pointing north and south, it's going to look different than east and west. So knowing the ellipticity of the beam, that's very important. The geometry of the beam. So if your beam is designed to be a Gaussian beam or a flat top beam, that's very important to measure and to verify. Focus spot location is really a big one. We're helping a lot of battery component manufacturers working with copper, which is a highly reflective, relatively difficult material to weld and to join. We're helping a lot of them with systems to verify that their focus spot is, number one, where it's designed to be, and that it stays there over the course of the process. It's very important to measure if there is any thermal effect on your laser system. That focus spot is going to change. We've seen that time and time again, unfortunately. So being able to verify the location. Those are just a few off the top of my head. Usually at the production stage, some customers like to see beam quality measurements like M squared, Rayleigh length, beam divergence. Some customers like to see that. I would say that those probably are not that important at the production stage. But again, I'm not a laser applications engineer by any means. And so, you may have different information that I do. But that information, laser quality information like that is usually more important on the source development and the application development, the system integration. So hope that answers that question.
Okay, let me find another question here. What is usually the component that causes the most problems in today's laser process?
Yeah, it's really interesting to investigate this. 9 times out of 10 today, it's going to be whatever component is closest to the process. So if you have a laser welding process and you have a cover glass that's going to protect the laser system from the brunt of the laser debris that flies around in the laser cell, that's probably going to be your culprit in most cases. So changing, monitoring that cover glass. Having said that, we have been involved with some customers that have a fresh cover glass, but they're still getting some focal drift. Investigate the laser system to find that there was an isolation optic that was dirty, that had been not been looked at for years, and it was extremely dirty. It just kind of been neglected. Cleaning up that isolation optic, putting it back in, solved the problem. So I would say work closest to your process and work backwards in your laser system, and you'll eventually find the culprit. But 9 times out of 10, it's probably the cover glass.
Okay. Next question. Don't today's lasers solve a lot of the problems that the older lasers used to have? That is, no more free space optics, bellows, etc.
They certainly do. And that kind of gets back to the comment that I made about the evolution of the laser system. Back in the good old days with the CO2 lasers, there were free space optics and there were bellows that kept the beam path clean. Those would fail and get a tear and completely trash all your optics and everything. So having that, the delivery fiber, the process fiber, having that light contained in those fibers has really helped with respect to beam quality. Not only that, the beam quality is so much higher with fiber optic lasers. But just having that light pipe, if you will, to have that has solved a lot of the problems. But having said that, that's not to say that there's a lot that can go wrong in those processing heads. They are engineered very well. They're very sealed. The laser the process debris really does have a tough time getting inside there, but that's not to say that it can't happen, especially when you open up that system to maintenance and things like that, that oftentimes can be a culprit of those changes. But yeah, in general, the laser system has been very well engineered over the years, and continuing to increase in performance and engineering.
Okay, we have time for one more question. I do want to mention to the audience that those questions that did not get, in fact, all questions, including the questions that did not get asked on air, will be sent to John, and he can answer them later at his leisure. So last question. Can you talk about the effects of the laser wavelength on the response of the measurement device and how Ophir is addressing the requirement from regulatory agencies to use multi-point calibrations instead of single-point calibrations?
It's a very good question, and I'll probably have to be honest with you, get back with you with somebody from calibrations to answer that point specifically. I know this is something that has been brought up in medical device manufacturing for quite a while. From an operational standpoint of our laser measurement products, I can say that thermopile sensors, which usually typically measure either single point energy or single pulse energy or continuous wave energy or average power, that really is kind of, most of those are broadband sensors that really don't, there is a calibration curve that's applied, but they really don't care with respect to the wavelength, what's being presented to it. That's different from pyroelectric sensors. There are single wavelength calibration points. Oftentimes what we do is we will calibrate those on with several different wavelength points, especially, and if there is a being careful not to say the wrong thing here. There have been concerns, or there have been requests from customers in the past that we do that, and so I'm gonna play it safe, and I'm gonna put you in touch with somebody who is more of authority on calibrations with respect to that. But that's a really, really good question. I thank you for that question.
All right. Well, the one question that I have left is: do you have any closing remarks you'd like to make?
Well, that's an easy one. Thanks, John. No, again, thank you for this platform to speak, John. I really do appreciate it. It is always a pleasure working with you and your team. I really do appreciate this platform to speak, and really do want to thank everybody who attended. And it's good to interface with you. Have a good day.
Okay. Well, I would like to thank today's speaker, John Mccauley of Ophir, for today's presentation, Laser Myths, What You Don't Know Can Hurt Your Process. I would like to remind you that the webinar on-demand version will be available on the Laser Focus World website, and the link to the archived webinar will be sent to you via email within the next 24 hours. On behalf of Laser Focus World and Endeavor Business Media, we thank you for joining us today and look forward to serving you with future webinars.
Bye-bye.